Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to design a concentrically loaded rectangular footing. A 450 by 300 mm interior column reinforced with 8 number 25 bars of grade 420 supports a dead load of 1000 kN and live load of 6 kN. Assume that the live load reduction of 25% may be allowed at the foundation level. The foundation is to be rectangular. As the column is rectangular, so most probably the footing will also be rectangular. So here it is restriction that the footing should be rectangular with the longer to shorter side ratio of 1.2 and placed at a depth of 1 meter where the gross allowable bearing capacity is 240 kilopascal. The average density of the backfill material and the footing concrete may be taken as 2100 kg per cubic meter, while the filling from the ground to plinth level is to be 0.7 meter with the average density of 1900 kg cubic meter. Design the footing using FC prime 25 megapascal and FY for the steel is 420 megapascal. Okay, first of all, we need to proportion our footing. We need to calculate the area of the footing. So for that, the area required of the footing is equal to service load divided by the net bearing capacity. So we can calculate the service load just by adding dead load and live load. So dead load is 1000 kilonewton and live load is 600 kilonewton. And we are given that the live load can be reduced by 25%. So we need to multiply it with the factor 1 minus 0.25, so it will give us 0.75 factors. So the service load is 1450 kilonewton and the net allowable bearing capacity is the allowable bearing capacity minus the depth of backfill multiplied by the density of backfill plus the depth of surcharge multiplied by the density of discharge. And as the density is in kilogram per cubic meter, so we need to convert it into kilonewton. So to convert this kilogram into kilonewton, we need to multiply it with the 9.81 and divide it by 1000. Convert this kilogram to newton, we need to multiply by 9.81, and then to convert into kilonewton, we need to divide it with 1000, because here the capacity is in kilopascal. It means kilonewton per meter square. So we also need to convert this into kilonewton per meter square. So for that we will multiply it with 9.81 and divide with 1000. So from here we can calculate the net bearing capacity. So once we have the net bearing capacity and the service load, so we can get the required area. So it comes out to be 6.69 meters square. And in the statement it was given that the length of the footing should be equal to 1.2 times the width of footing. So it means area, which is equal to L into B. So we can write area is equal to 1.2 B times B, or 1.2 B square. So area, which is 6.69. So from here we can calculate the value of B, so which is 2.4. So if B is 2.4, then L will be equal to 1.2 times 1.4, which is 2.8. Sorry, it is 2.4. So it will be 2.8. So from here we can calculate, or we can proportion our footing with width 2.4 meter and length 2.8 meter. So once we have proportioned our footing, then the next step is to calculate the net soil pressure under the footing. So for that, the net soil pressure is given by the factored applied load divided by the area of footing. So we need to calculate this factored applied load. So 1.2 dead load plus 1.6 live load. So 1.2 into 1000 plus 1.6. This factor is for reduction of the live load multiplied by 600 live load. So it will give us the factored applied load. So factored applied load divided by the area of footing, it will give us the net soil bearing pressure under the footing. So we are bearing pressure under the footing slab. Okay, after that we need to estimate the thickness of footing. So for that we can use this expression. We have discussed this expression in the previous videos. So Here P and M, these are the service loads and service moments, so we need to substitute the service load value. So P, we have already calculated service load, which is 1450, and it was in kilonewton, so to convert it into newton we need to multiply it with 1000 divided by 0.01, and alpha for interior column, if column is at the center of the footing slab, so then its value will be 40, if at the edge then 30, and if at the corner then 20. So in our case it's at the center, so in that case its value will be 40, and FC prime 25 plus 60, so it will give us the H value. It is 441, so we can either select 450 value or we can also select some higher value 500. So we can first perform the trial by using this value. If it fails to resist the punching shear, or if this thickness is insufficient for the punching shear and direct one-way shear, so in that case we need to increase the value. But in this example we will directly select some higher value, which is 500 millimeter. So if H is 500 millimeter, we can calculate the effective depth H minus 60. This 60 is actually, we assume that the clear cover is about 50 and the diameter of the bar which we are using as a reinforcement, flexural reinforcement of the footing is about 20 millimeter. So in that case it will be 10 millimeter, half of the diameter. So we can subtract this 60 value out of this H, or otherwise based on the clear cover as well as the diameter of the selected bar we can calculate the exact value instead of this 60. So here we have used 60 and it will give us the effective depth of 440 millimeter. Okay, once we have the depth and the thickness of the footing, now we need to check that thickness for punching shear as well as for one-way shear. So for punching shear, the VU applied punching shear should be less than the punching shear capacity of the footing slab. So to calculate the punching shear capacity of the footing slab phi C VC, the three equations are given in the ACI code. So the lesser of these three values, or the lesser value out of these three equations will be considered as the shear capacity of the footing slab to resist the punching or two-way shear. So in this, if we see in this equation, so we need the value of B naught, which is the critical dimension or perimeter of critical section. So if we see our footing is like this, so we have column over here. So the critical section will be at a distance d by 2 in case of punching shear from the face of the column. So d by 2 on this side and d by 2 on this side. Similarly, d by 2 on this side and d by 2 on this side. So the perimeter, so this dimension will be C1 plus D, mean d by 2 on one side and d by 2 on the other side. Similarly, this dimension will be C2 plus D. So if we find the perimeter, so it will be 2 times C1 plus D and C2 plus D, or we can say C1 plus C2 plus 2D. So from here we can find the dimension or value of the critical parameter, or we can find the value of parameter of critical section. So the next value that we need is D, which we have already calculated 440. We also need this B value, which is the ratio of longer side of the column to the shorter side of the column. So 450 longer side of the column and 300 the shorter side, means C1 over C2. It is equal to beta. We also need this lambda, which is 1 for normal weight concrete, and in our case we are using normal weight concrete, so its value will be 1. And we need this alpha, and its value is 40 for interior columns, and remaining factors are the same. So we can substitute these values to evaluate these three equations to get the capacity of the shear capacity of the footing concrete. So the lesser of these three, which is 75 kilonewton, so this will be the shear capacity of the footing concrete. Okay, after that we need to calculate the applied shear value VU. So applied shear value VU is given by, so if we have this footing and the column is over here, this is the critical section. So the load outside this critical section, or the pressure, contact pressure outside this critical section multiplied by the area of the footing outside this critical perimeter or critical section will give us the VU value, the applied punching shear. What it means? If the pressure under this footing is QU, then multiplied by the area of the footing minus the area of this critical section, or area of the footing in between this critical section. So which is actually, if I term it as B1 and this as B2, so it will be B1 times B2, and here B1 is equal to C1 plus D and B2 is equal to C2 plus D. Okay, so by using this expression we can calculate the applied punching shear. So QU times area of footing minus C1 plus D and C2 plus D. So by substituting these values we can calculate the value of applied punching shear, which is 1732, and it is less than the punching shear capacity of the footing slab. So it means our selected depth of the footing is adequate to resist the applied punching shear. After that, we need to check for the one-way shear. We need to investigate whether the selected depth of the section or selected depth of the footing slab is adequate to resist the one-way shear value. So again, for that, VU should be less than 5 VC. This VU is applied one-way shear, and this 5 VC is the shear capacity of the footing slab against one-way shear. So we can calculate the VU value, the maximum applied one-way shear for flexure. So we will calculate it for unit width. So for that, again, we need to look at the section. So here, if we have this column, so the critical section will be at a distance D from the face of the column. So here we can select a unit width having width 1000 millimeter or 1 meter, and then we need this much length, the span of the cantilever portion beyond this critical section. So if this total is L and this one is C1, so and this much is D, then we can determine this span. For example, I call it as small l. So L is equal to L by 2 minus this C1 by 2 minus D. So it will give us this value L. So this span multiplied by the pressure under this footing slab, it will give us the value of one-way shear, one-way applied shear for unit width. So QU, the applied shear value, applied contact pressure under the footing, L by 2 minus C1 by 2 minus D. So L by 2, 2.8 by 2, and 450 is the dimension C1, so 0.45 divided by 2, and 440 is D, so 0.44. So it will give us the value of one-way shear, and remember this is for unit width because we have multiplied with 1 meter. So this value will be for unit width of footing slab. Okay, then we need to calculate the capacity for the unit width of footing. So here the capacity is given by 0.75 times 1 by 6 or 0.17 times square root FC prime times B into D. So 0.75 over 1 over 6, 25 square root, and here B will be equal to 1000 because we are considering unit width strip, multiplied by the D, the depth of the footing, divided by 1000 to convert it into kilonewton. So it will give us the value of the resistive shear or the shear capacity of the footing slab. So it is 275, and this 275 is more than 210 the applied shear. So it means the capacity of the section against one-way shear is more than the one-way applied shear. So our selected depth of the footing is adequate to resist the one-way shear as well. So after that, we need to calculate, or we need to design for the flexure. So we need to calculate the bending moment in the longer direction as well as bending moment about the shorter direction. So for that, we consider that our critical section is at the face of the column. So in longer direction, the critical section will be at the face of the column. So to calculate the bending moment in unit strip, we will consider again unit design strip. So we considered it as a cantilever beam subjected to uniformly distributed load. So the uniformly distributed load will be QU times 1, and the length of this cantilever beam will be equal to this L total length, and this much we can call it as LL, the span in the longer direction. So LL will be equal to L minus C1 divided by 2, or we can write L by 2 minus C1 by 2. So it will be equal to L minus C1 by 2. So from here we can calculate the span in the longer direction. So once we have span in longer direction and the load on this cantilever span, which is equal to QU into 1, so we can calculate the bending moment. So M is equal to QU into span LL into L by 2. So it will give us QU into LL square divided by 2. So which is written over here, QU into LL square divided by 2. So similar procedure will be adopted for the shorter direction. So here this LL will be replaced with S, and this L will be replaced with B, and C1 will be replaced with C2. So this will be the shorter span, B minus C2 divided by 2, and once we have this shorter span, we can easily calculate the moment in the shorter direction. So the cantilever span in the shorter direction, B minus C2 divided by 2, so it comes out to be 1.05, and the span in the longer direction, it is L minus C1 divided by 2, so it comes out to be 1.175 meter. So from here, by using these two spans, we can calculate. So here it is longer instead of shorter. We can calculate the bending moment, QU into LL square by 2, it is 197.24, and in the shorter direction it is 157.5. So once we have the bending moments, the next step is to calculate the longitudinal steel and longer steel as well as the shorter steel, means steel in the longer direction and steel in the shorter direction. So to calculate the steel in the longer direction, we need the MU value, mean moment along the longer direction. We need to calculate raw value, which is W into 1 minus square root 1 minus 2.1614 R over FC prime. So here W is equal to 0.85 FC prime divided by Fy. We have already studied this many times, and R is equal to Mu over BD square. So from here we can calculate Mu over BD square, its value is 1.0188, and then we can calculate the raw value. So once we have the raw value, we can calculate the area of steel, raw into BD, mean area of footing slab. So here we are considering unit width, so B will be equal to 1 meter, and D is the depth of the footing, effective depth of the footing. So this reinforcement ratio multiplied by P multiplied by D, so it will give us the area of steel required for 1 meter width of the footing slab. So once we have the area, so we can calculate the spacing. We also need to check that this area should be more than the minimum areas. For 420 steel, the minimum reinforcement ratio is 0.0018, so multiply it with B into H, so it will give us 900 millimeters square. So the calculated area is more than the area minimum, so we will use this calculated value. So now the next step is to calculate the spacing of the steel bars. So for that, first we need to select that which bar should be used as a reinforcement. So for example, we select number 16 bars. So spacing will be equal to area of bar divided by total area of steel multiplied by 1000 if we are using 1 meter width, or if this AS is for 1 meter width. So AB will be equal to 200 for 16, and this is 1232 multiplied by 1000, so it will give us the S value, which is 160 millimeter. So we need to round down the value. Its value comes out to be actually 161, so we need to use some lower values, so we can use 160 millimeter as the spacing, center to center spacing between the bars. Similarly, we need to calculate the reinforcement in the shorter direction, so we need to use Mu of shorter direction, Mu over BD square, then we can calculate raw value, and then from this raw we can calculate the area of steel, and this area of steel is again for unit width of the member. And we need to compare it with the A minimum. So A minimum is 900, so calculated area is more than this minimum, so we will use this area. So in case of rectangular footing, we need to provide the shorter reinforcement in such a way that in the central band, this is the column, So in the central band having width equal to B, we need to provide some larger reinforcement we need to provide some larger reinforcement as compared to these edges, and the amount of reinforcement to be provided in this bandwidth should be equal to 1 over B plus 1. So 2 over B plus 1 times total reinforcement. So reinforcement in bandwidth will be equal to 2 over beta plus 1 into total reinforcement. So we need to distribute or find out the value of the reinforcement that need to be provided in the central band. The reinforcement distribution in the shorter direction, so central band width will be equal to B, which is 2.4 meter or 2400 millimeter, and beta is the ratio of longer to shorter side of the footing, mean 2.8 divided by 2.4, so it is 1.17. Okay, the reinforcement in the central band should be equal to 2 over beta plus 1 into total amount of reinforcement. So 2 over beta plus 1, so this factor will become 0.923, and total reinforcement, we have already calculated the reinforcement in the shorter direction for 1 meter width, which is 1012, and the total width in the shorter direction is 2.8. So if we want to calculate the total reinforcement, so we need to multiply this 1012 with the 2.8 total width of the footing. Initially we calculated this value for unit width. So if we want to find the total reinforcement that need to be provided in the shorter direction, so we need to multiply it with this factor, which is, or this length, which is 2.8 meter. So it will give us the value of total reinforcement to be provided in the shorter direction. And if we want to convert this into the reinforcement that need to be provided in the unit width in the central band, for example, this is the central band, and the reinforcement to be provided in the unit strip of central band, so we need to divide it with the width of the central band. So here this factor is to calculate the total reinforcement in the shorter direction, and then we divided it with the 2.4, the width of central band, to calculate the reinforcement that need to be provided in the central band per meter width. So once we have this reinforcement per meter width, then we can calculate spacing, which will be equal to area of bar divided by area of steel multiplied by 1000. So from here we can calculate the spacing of the bars and the diameter of bar. Okay, so this is the reinforcement that need to be provided in the central band. So to calculate the reinforcement that need to be provided outside the central band, so we need to calculate that reinforcement. So reinforcement in the outer band will be 1 minus 2 over B plus 1, beta plus 1 into total reinforcement. It means the amount which we have provided over here in the central band out of the total reinforcement, the remaining will be provided in the outer band. So for that, 1 minus 2 over beta plus 1. So 1 minus 0.923 times the reinforcement required for unit width and multiplied with 2.8 to calculate the total reinforcement. Okay, and then divide it to convert it into the reinforcement required per unit width. Or if we don't want to convert it into unit width, so no need to divide it with this one, so just calculate the value. So it comes out to be 218 millimeter square for the total outer band. Mean this is the central band, so this is 2.4 and total is 2.8. So 0.2 meter on this side and 0.2 meter on this side, so total 0.4 meter. So this much reinforcement to be provided in the outer bands, mean in the total width of 0.4 meter. So from this we can calculate the number of bars. To directly divide this area with the area of one bar. For example, if we use number 13 bar, so the area of number 13 bar will be close to, I think, 120. So if we divide this with 120, so we will get the number of bars, that this much number of bars need to be provided. So if we divide, it will be close to 2, and it means we need to provide 2 bars in this much width. So 1 bar on this side as well as 1 bar on this side. So in this way we can calculate the reinforcement to be provided in the outer outer bands. So once we have decided the reinforcement that need to be provided in the inner band or central band and the outer band, the next step is to check for the bearing. So bearing strength of footing as well as bearing strength of column. So for that, first we need to check the bearing stress and dowel requirement within the foundation. So for that we need to calculate the bearing strength to be provided by the foundation concrete. That is given by 0.85 Fc prime into area of column multiplied by square root of A2 over A1. And this should be less than 2 times 0.85 Fc prime, 0.85 Fc prime A1. So here if we see this A1 is equal to area of column, which is 135,000, or we can say it is equal to 450 multiplied by 300. And A2 is, we can calculate this A2 by using this technique as I have explained earlier in the previous videos, that first we need to see what is the least projection from the face of the column, or the least projection of the footing slab from the face of the column. So we need to calculate this value. So this total is 2800, this total is 2400. So the projection on one side, on this side 2800 minus C1 which is 450 divided by 2, so it is 1175. So the projection on this side and this side is 1175, and on this side it is 880. Sorry, we need to calculate this one. It is 2400 minus 300 divided by 2, so it is 1050. So we need to select the least value out of these two projections. The least value is 1050. So 1050, so we need to compare it with the 2 times of D, and 2 times of D is 440 multiplied by 2, so it is 880. So we need to select the least value out of these two, mean this least projection and 2 times of D. So 880 is the least value out of this. So now we need to calculate the area at this level, which will be equal to, if this is the column over here, so 880 on this side, 880 on this side, 880 and 880. So this dimension will become C1, 880, C1 and 880. So it will be 880 times 2 plus 450. And similarly this dimension will become 880 times 2 plus 300. So by using these two dimensions, by multiplying these two dimensions, we can calculate the A2, and this A2 will comes out to be 455 to 600 millimeter square. So first we need to find the least projection on on all four sides. Once we have the least projection of the footing slab from the face of the column, then compare it with the 2D and select the least value out of this 2D and the least projection out of all four sides. For example, if this 2D is least, then the projection on all four sides will be equal to 2D from the face of the column, and then calculate the dimension of this area at this level, and then calculate the area A2. Okay, so this area A2 and A2 over A1 ratio, square root of that will comes out to be 5.81, and it should be less than 2. So we can use this expression to calculate the phi Pn, the bearing strength provided by the footing concrete, and it comes out to be 729 kilonewton. And the next is we need to check whether the dowel reinforcement is required or not, or the bearing strength to be provided by the dowel inside the footing. So for that, the load that must be resisted by the dowel reinforcement is equal to Pu, the applied load, minus the load resisted by the footing concrete. So applied load is 1920 and the resistance provided by the concrete is 3920. So its answer will come negative. So it means we don't need any dowel reinforcement. The concrete alone is enough to bear the applied loads. So the next is we need to check for the bearing stress and dowel reinforcement within the column. So for that we need to check how much resistance will be provided by the column concrete. So that is phi 0.85 Fc prime A1. So phi is 0.5 in case of bearing, 0.85 Fc prime, and A is 450 by 300. So it comes out to be 1864.7 kilonewton. And then we need to check how much load will be resisted by the dowel reinforcement, that is Pu minus 5Pn. So it is 1920 minus 1864, so 55.3 kilonewton load will be resisted by the dowel reinforcement. So for that load we can calculate the area of the dowel reinforcement, that is equal to load resisted by the dowel reinforcement divided by phi Fy. So phi is 0.65 and Fy is 420. For the dowel reinforcement, Pu is 55.3 kilonewtons multiplied with 1000 to convert it into Newton. So we will get the area of dowel reinforcement. So corresponding to that area we can calculate the number of bars. For example, we use number 16 bars, so we need to divide it 2 with the area of the number 16 bar, which is 200. So it means 1 bar is sufficient. We also need to check for the minimum area of steel required for the dowel, which is 0.005 times area of column, and it comes out to be 675, and it is more than this calculated value, so this minimum value will prevail. So for this minimum value we need to calculate the number of bars. So 675 divided by 200, so it will give us answer 3 point something or 3.05 or something. So it means we need 3 or more than 3 bars. So we can use 4 bars of 16 millimeter diameter as a dowel reinforcement. But the preferable is we need to provide as many dowel bars as the number of bars in the column. So our column has 8 number 25 bars, so we need minimum 8 bar as a dowel reinforcement. That is preferable. So we can use 8 number 16 bar as a dowel reinforcement. Although it is more than the required, but we need to use this 8 number 16 bar as a dowel reinforcement. Okay, after that we have checked all the limitations. We have satisfied our footing slab against all the failure modes. So the next is to communicate the design. So for the communication, we need to communicate the length and width or the section details, so which is 2.4 width and 2.8 length of footing. And then we need to show the reinforcement detailing. So in longer direction we have uniform distribution of the reinforcement, which is equal to number 16 bar at the rate of 160 millimeter. But in the shorter direction, in the central band starting from here up to here, we need a larger amount of reinforcement, which is equal to this much, number 16 bar at the rate of 180 millimeter. And the width outside this central band, we have calculated that we need to provide one number 13 bar on each side. So this is the reinforcement detailing for the footing slab. Similarly, we need to detail for the dowel, and then dowel reinforcement will be shown in the section. So we need to provide this dowel reinforcement, and this dowel reinforcement is 8 number 16 bar. We can also provide the temperature reinforcement at the top. We can provide the minimum reinforcement at the top for the shrinkage creep as well as for temperature.